Back in 2017, astronomers spotted something racing through the solar system that didn't belong here. It wasn't bound to the sun like an asteroid or a comet. It was just passing through. That object was named ʻOumuamua, and it left scientists scratching their heads. It didn't behave like any comet we'd ever seen. No glowing tail, no obvious gas jets. Yet it somehow sped up slightly, as if something was pushing it. Its shape was also bizarre, possibly cigar-like or pancake flat, depending on how you interpret the data. And because it was already on its way out when we noticed it, telescopes only got a brief look before it disappeared forever. Then in 2019 came 2I/Borisov. This one looked familiar. A classic comet, venting gas and dust with a bright tail stretching across the sky. It suggested that maybe Oumuamua was just a strange outlier. But in 2025, astronomers announced a third interstellar visitor, 3I Atlas. Unlike Oumuamua, it was spotted earlier in its approach, giving us time to watch it closely. And unlike Borisov, its behaviour so far is raising new puzzles. With 3 examples now on the books, we're finally able to compare, not just speculate. And what 3I Atlas is revealing could completely reshape how we think about visitors from other star systems. When Oumuamua was first detected by the Pan-STARRS telescope in Hawaii in October 2017, the discovery immediately sparked a sense of urgency in the astronomy community. Here was the first confirmed object from another star system, passing through ours, and it was already on its way out. Astronomers scrambled to point every available telescope at it, knowing they had just a few weeks before it became too faint to study. The limited data we managed to collect set the stage for years of debate and speculation, because the object simply didn't behave like anything we'd seen before. The first mystery was its trajectory. The hyperbolic orbit was a clear signature that this thing wasn't from the solar system. Its eccentricity was about 1.2, slightly above the threshold of one that marks an unbound orbit. That meant it was moving too fast to ever return. But on top of that, researchers noticed that its path was deviating just a little from the course predicted by gravity alone. The shift wasn't huge, but it was measurable, roughly a few tens of meters per second of extra push. That immediately raised the question, what was accelerating it? For a comet, the answer would normally be gas jets from sublimating ices. When ice turns to vapor under the sun's heat, it vents outward and nudges the comet in the opposite direction, just like a weak rocket thruster. The problem was telescopes couldn't see any trace of outgassing. No coma, no tail, nothing. The second puzzle was its brightness and shape. Astronomers tracked how its brightness changed as it rotated, and the variation was extreme, much greater than for most asteroids or comets. That implied an elongated or flattened shape, with estimates ranging from something like a 200-metre cigar to a 40-metre pancake. Both were unusual compared to the population of solar system objects we know, which tend to be more compact and irregular rather than strongly stretched. Some models suggested it could have been a shard, perhaps fractured off a larger body. But again, without direct images, all anyone had were indirect brightness curves and assumptions. The third major mystery was its surface and composition. Oumuamua reflected sunlight in a way that hinted at a reddish surface, not unlike many outer solar system objects. That could mean it had been exposed to cosmic rays in interstellar space for millions of years, chemically altering its surface into darker, more carbon-rich compounds. But the real kicker was the acceleration. If there was no gas being vented, what else could explain the extra push? This is where the more exotic theories began to appear. Some scientists proposed that Oumuamua might have been made of unusual ices, like pure hydrogen or pure nitrogen, that could sublimate invisibly. The hydrogen iceberg idea, for instance, suggested it could have formed in the dense clouds of giant molecular regions, only to erode during its passage. The nitrogen hypothesis imagined a chunk chipped off the surface of a Pluto-like exoplanet. Both ideas faced challenges, mostly about whether such ices could survive long enough in interstellar space without eroding away. Then came the solar sail idea, most famously advanced by Avi Loeb. If Oumuamua was a thin, light structure, like a reflective sheet, then sunlight pressure could have explained its acceleration. Loeb went so far as to suggest it could be an artificial object, maybe a probe or a fragment of alien technology. That claim grabbed headlines, but the majority of astronomers were cautious. Most felt there had to be a natural explanation that didn't require jumping to extraterrestrial engineering. Still, the fact that it couldn't be easily explained with standard comet or asteroid models left the door open at least a crack to more speculative thinking. Complicating matters further was how late it was discovered. By the time telescopes were turned on it, ʻOumuamua was already moving away from the sun and fading quickly. No spacecraft were anywhere near close enough to intercept it, and no planned mission could have launched in time. So astronomers had to make do with limited data. Just a few weeks of brightness curves, spectra, and trajectory measurements. It was like trying to solve a crime with a handful of blurry photos. In the years since, computer models have explored various scenarios. Maybe ʻOumuamua was a fragment of a tidally disrupted planetesimal, stretched and flattened during its journey past its home star. Maybe it was covered in a protective crust that sealed in its ices, allowing for sublimation in ways that didn't produce a visible coma. Or maybe it really was an extreme outlier in shape and composition, one we just happened to catch by chance. What's clear is that ʻOumuamua forced astronomers to reconsider what normal interstellar objects might look like. Before 2017, the assumption was that if we ever saw one, it would behave just like a comet from our own Oort cloud. Instead, the first example broke the rules. That's why, when 2I/Borisov appeared just 2 years later, it was such a relief. Finally, something that looked familiar. But now, with 3I Atlas in the picture, astronomers can start asking deeper questions. Was ʻOumuamua the odd one out? Or are we only beginning to see how diverse interstellar visitors can be? In early September 2025, astronomers detected the third confirmed interstellar object, 3I Atlas. The discovery came from the Asteroid Terrestrial Impact Last Alert System, ATLAS survey, a pair of telescopes designed to scan the sky for potentially hazardous asteroids. These instruments, stationed in Hawaii and Chile, continuously map wide swaths of the sky, looking for anything that moves against the backdrop of stars. When one such moving point of light was flagged, follow-up analysis showed it wasn't following the bound elliptical path of a solar system body. Its orbit was hyperbolic, a telltale sign that it wasn't from here. What made this find particularly exciting was its timing. Unlike ʻOumuamua, which was already on its way out of the solar system when discovered, 3I Atlas was caught on its inbound leg, still months away from perihelion. That gave astronomers an early start to track it as it brightened, allowing for coordinated observations across the globe and with space telescopes. This was a chance to avoid the mistakes of ʻOumuamua. No last-minute scramble, no fading into the darkness before the data were conclusive. Almost immediately, pre-covery images were identified, older observations in which the object had been photographed but not recognized at the time. These allowed researchers to refine its orbit with surprising accuracy. The numbers made it clear. This was interstellar, moving at more than 25 kilometers per second relative to the Sun on approach, with an eccentricity well above 1. Unlike Borisov, which had been discovered by a single amateur astronomer, Atlas was found by an automated system, a reflection of how far sky surveying technology has come in just a few years. Wide-field surveys now generate massive amounts of data each night, and software combs through it for moving objects. The fact that an interstellar comet turned up in that data shows both the power of automation and the reality that these visitors may be far more common than we once thought. News of 3I Atlas spread quickly, and within days, major observatories and space agencies were scheduling time to observe it. The James Webb Space Telescope, Hubble, and ground-based facilities in Chile and Hawaii all prioritize follow-ups. Even ESA missions like Mars Express and JUICE were tasked with opportunistic observations from their unique vantage points. The goal was simple: gather as much information as possible before Atlas swung past the Sun and disappeared into deep space. The discovery also sparked discussions of whether a spacecraft interception was possible. By 2025, proposals for interstellar interceptor missions were already on the table, motivated by the missed opportunity with ʻOumuamua. Some designs envisioned a probe on standby, ready to launch quickly if another interstellar object appeared. But Atlas was discovered too late for a dedicated spacecraft to catch up. Its speed and trajectory made any intercept mission unfeasible with current launch capabilities. For now, telescopes would have to do the work. In just weeks, early observations began to hint at activity. A faint coma, signs of outgassing, and dust being released into space. That immediately set Atlas apart from ʻOumuamua, which had shown no visible activity, and aligned it more with Borisov. But the details didn't quite fit neatly into either category. Astronomers were watching closely, because this comet might finally help resolve whether ʻOumuamua was a strange anomaly, or whether interstellar visitors come in a wide range of unexpected forms. The first thing astronomers do after identifying a new comet is work out its orbit. With 3i Atlas, the calculations left no doubt. This was an interstellar visitor. Its eccentricity was around 1.35, far above the break-even point of 1 that separates bound orbits from unbound ones. That number alone told researchers it wasn't just another Oort cloud comet perturbed by a passing star. It had come from outside the solar system entirely. Its inbound velocity relative to the Sun was measured at about 26 kilometers per second. A blistering speed, but consistent with what you'd expect from an object wandering the galaxy on a random trajectory. Combined with its outbound speed, that velocity indicated that Atlas had been coasting through interstellar space for millions, if not billions of years, before crossing paths with our solar system. The geometry of its arrival was also unusual. Its inclination was steep relative to the plane of the planets, which meant it wasn't skimming along the ecliptic where most solar system bodies travel. Instead, it came in from a tilted angle, another piece of evidence confirming it wasn't native. By backtracking its path through space, astronomers tried to identify a possible origin star system, but the uncertainties in velocity and the chaotic gravitational influences of the galactic environment made that nearly impossible. As with ʻOumuamua and Borisov, the best we can say is that Atlas probably came from somewhere in the local galactic neighbourhood, ejected from its home system long ago. Perihelion, the point of closest approach to the Sun, was set for December 2025 at a distance of about 0.8 astronomical units, slightly inside Earth's orbit. That made it both accessible for telescopic observations and bright enough to study in detail. Its minimum distance from Earth, however, wasn't particularly close, about 1.5 astronomical units at best. So while it was never going to be a spectacular naked-eye comet, it was bright enough for large telescopes to probe its composition. The trajectory also raised practical challenges. Atlas wasn't just fast, it was on a one-time flyby, never to return. That meant astronomers had a strict deadline. Observations had to be made during the narrow window when the comet was near the Sun and relatively bright. Once it left perihelion, it would fade quickly as it accelerated outward, eventually vanishing back into the depths of interstellar space. What excited many researchers about the orbital analysis was how it compared to the first two interstellar objects. Oumuamua had arrived on a hyperbolic orbit with a slightly lower eccentricity, and its non-gravitational acceleration complicated the fit. Borisov had a clean cometary orbit, but with less time for pre-covery refinement. Atlas, by contrast, offered the best of both worlds. A clearly interstellar trajectory, discovered early enough to allow precise orbital solutions, and with plenty of time for telescopes worldwide to observe it across its journey. In other words, 3i Atlas provided not just another data point, it was the best chance yet to track an interstellar comet under ideal observing conditions. That made it a benchmark object, one astronomers hoped could finally put the debates sparked by ʻOumuamua on firmer ground. One of the most valuable aspects of 3i Atlas's discovery was its timing. Unlike ʻOumuamua, which was spotted on its way out of the solar system, Atlas was identified months before perihelion. This gave astronomers a rare opportunity, the ability to plan, schedule, and execute coordinated observations while the comet was still inbound. That extra lead time meant that telescopes on Earth and in space could follow its entire journey around the Sun, from approach through closest passage and into its outbound leg. Perihelion occurred in December 2025, when Atlas swung in to about 0.8 astronomical units from the Sun, slightly closer than Earth's average orbit. That distance placed it well within reach of the most powerful telescopes, but not so close that the Sun's glare completely overwhelmed the view. Unlike Borisov, which grazed deeper into the inner solar system, Atlas took a path that was convenient for astronomers, close enough to brighten substantially, but far enough to allow continuous monitoring. In terms of planetary encounters, Atlas never came particularly close to Earth. Its minimum approach was roughly 1.5 astronomical units, meaning there was no chance of a close flyby or visible naked-eye spectacle. For comparison, that's about the same distance Earth is from Mars at opposition. Still, its relative brightness and distinctive trajectory made it a prime target for spectroscopic and imaging campaigns. Even though backyard astronomers weren't going to see a dramatic comet tail stretching across the sky, professional instruments had no trouble gathering the high-quality data needed. Timing also worked out in terms of observational assets. By late 2025, the James Webb Space Telescope was in its third year of operation, fully capable of probing Atlas's composition in infrared detail. The Hubble Space Telescope, though aging, was still operational and added ultraviolet coverage. Meanwhile, ESA was able to take advantage of its planetary spacecraft, Mars Express and JUICE, to make opportunistic observations from different vantage points. Having multiple instruments spread across the solar system gave astronomers the ability to study Atlas in ways that hadn't been possible for ʻOumuamua. Another factor was seasonal geometry. From Earth's perspective, Atlas was well placed in the night sky during much of its approach and retreat, not hidden behind the sun for extended periods. This accessibility meant continuous monitoring was possible, allowing astronomers to track the evolution of its activity over weeks and months, rather than catching just a snapshot at peak brightness. All of this combined to make Atlas the most favourable interstellar object yet for observation. ʻOumuamua arrived with almost no warning, and Borisov, while studied in detail, had less ideal geometry and a shorter bright phase. Atlas was different. Its orbit, timing, and proximity to the Sun created the best conditions so far for answering the big questions about what these visitors are made of, how they behave, and how they compare to the comets and asteroids born in our own system. From the moment 3I Atlas was confirmed as interstellar, observatories around the world and in space began targeting it. This was the first time astronomers had the luxury of planning observations in advance for an object like this, instead of scrambling after the fact. With months to prepare, a wide range of instruments, from small ground-based telescopes to flagship space observatories, were put on the case. On the ground, major facilities in Chile, Hawaii, and the Canary Islands monitored Atlas in multiple wavelengths. Wide-field survey telescopes like Pan-STARRS and the VLT survey telescope tracked its brightness changes, while larger instruments such as the Very Large Telescope and Keck Observatory provided high-resolution spectra. In the radio range, ALMA in Chile searched for signatures of molecules released as the comet warmed near the Sun. These observations built a detailed timeline of how Atlas evolved as it approached perihelion. In space, the James Webb Space Telescope became the star player. With its infrared sensitivity, JWST could detect molecules like carbon dioxide, methane, and water vapor. Substances often difficult or impossible to study from the ground, because Earth's atmosphere blocks those wavelengths. Early reports confirmed the presence of carbon dioxide outgassing, an important clue about Atlas's makeup. Hubble contributed too, particularly in ultraviolet wavelengths, giving coverage JWST cannot provide. Even more uniquely, ESA leveraged its planetary spacecraft to catch Atlas from other perspectives. Both Mars Express and JUICE turned their cameras and instruments toward it, providing vantage points unavailable from Earth. The coordinated observing campaign made Atlas the best-studied interstellar visitor yet. By combining data across the spectrum, infrared, optical, ultraviolet and radio, astronomers could start piecing together a comprehensive picture of its size, activity, and chemistry. Naturally, the discovery also reignited discussions of a spacecraft intercept. After the missed opportunity with ʻOumuamua, several mission concepts had been proposed. One of the most prominent was the idea of a ready-to-launch interstellar interceptor, a spacecraft that would sit in storage, waiting to be launched at short notice once the next object was detected. In theory, 3I Atlas could have been a candidate, but in practice, it was discovered too late to mobilize such a mission. Even if a spacecraft had been ready, Launching, matching velocity, and intercepting Atlas would have required extraordinary delta V, essentially more than current rockets can deliver. Still, 3I Atlas has played a major role in pushing these mission concepts forward. Space agencies can now use the lessons from this comet to refine their designs. They know how much warning time is needed, what sort of instruments would be most useful, and how an interceptor could be positioned in advance to maximize its chances of success. In that sense, Atlas may be the catalyst that finally turns what-if mission studies into concrete projects. For now, though, telescopes remain our only option. Fortunately, 3I Atlas has turned out to be cooperative in that regard. It's bright enough to be studied in detail, its orbit favourable enough to keep it accessible, and its activity strong enough to reveal its chemistry. As astronomers continue to analyse the data, Atlas is already shaping up to be the most informative interstellar object we've seen so far. One of the first questions astronomers asked after confirming 3I Atlas was simple. Does it behave more like ʻOumuamua or like Borisov? That is, would it stay oddly inert, with no signs of outgassing, or would it display the classic features of a comet? Observations quickly provided the answer. Unlike ʻOumuamua, Atlas began showing activity almost immediately. A faint coma, the fuzzy cloud of gas and dust that surrounds an active comet, was detected within weeks of discovery. As it drew closer to the Sun, the activity increased. Dust particles were pushed away by solar radiation, creating a visible tail. But in a surprising twist, astronomers noticed that some of the dust wasn't streaming away in the usual anti-solar direction. Instead, portions of the material seemed to be directed sunward, a sign of complex dynamics in how gas and dust were escaping the nucleus. This hinted at jets erupting from specific regions on the comet's surface, shaped by its rotation and the uneven distribution of volatile materials. By tracking the coma, researchers could infer the size of the dust grains and the rate at which material was being ejected. Estimates suggested Atlas was shedding several kilograms of dust every second as it warmed, comparable to modest comets in the solar system. This level of activity was enough to give astronomers excellent data, but not so much that the comet threatened to fragment catastrophically, as some fragile comets do when approaching the Sun. The coma also provided key clues about the comet's structure. The brightness and colour of the dust indicated a mix of silicates and organics, similar to comets in our solar system, but with subtle differences in reflectivity. These distinctions may point to variations in how Atlas formed in its original star system. Just as Borisov's high carbon monoxide content suggested a birthplace in an unusually cold environment, Atlas's coma chemistry could reveal details about its home. Another advantage of having an active coma is that it makes spectroscopy possible. When sunlight passes through the gas surrounding the comet, it leaves absorption and emission lines in the spectrum, like a fingerprint of its molecular makeup. Already carbon dioxide and water vapour have been confirmed. More sensitive instruments are searching for carbon monoxide, ammonia, and trace organics. Each detection helps narrow down the range of possible formation scenarios. Comparisons with Borisov are inevitable. Borisov produced a much denser coma and an extremely long tail, making it visibly comet-like, even in amateur telescopes. Atlas, while clearly active, seems somewhat less dramatic, more subdued. That might suggest it is smaller, or that it carries fewer super-volatile ices. But the fact that it is active at all is critical. It confirms that ʻOumuamua was indeed unusual. The first interstellar object wasn't representative of the whole population. With 3 examples now in hand, we can start to see a spectrum. One inert and strange, one very active, and one somewhere in between. For astronomers, that diversity is the real prize. It means we're not just looking at clones of the same thing over and over. Interstellar visitors may span a wide range of sizes, compositions, and activity levels. And Atlas, by showing clear signs of being an active comet, provides a crucial anchor point in that spectrum. One of the most exciting aspects of studying 3I Atlas is the ability to measure what it's actually made of. With ʻOumuamua, astronomers had only brightness curves and trajectory data to work with, no clear signs of gas emissions. With Borisov, spectroscopy revealed a composition rich in carbon monoxide compared to solar system comets, pointing to a frigid origin environment. Atlas falls somewhere between these two extremes. It's active enough to reveal its chemistry, but its emissions look different from Borisov's. Early infrared observations with the James Webb Space Telescope confirmed carbon dioxide, CO2, outgassing, one of the strongest signatures so far. This detection is important because CO2 is difficult to observe from Earth, as our atmosphere blocks those wavelengths. JWST made it possible to isolate CO2 directly, showing that Atlas contains significant amounts of this volatile ice. Water vapour has also been identified, as expected for any comet warming up near the Sun. Together, these gases suggest Atlas's nucleus holds a mix of materials similar to solar system comets, but possibly with different ratios. What about carbon monoxide CO? That was the standout in Borisov, with levels far higher than typical local comets. For Atlas, the situation seems different. So far, CO emissions appear weaker, closer to the range seen in average solar system comets. If that result holds up with further analysis, it would mean Atlas formed in a less extreme environment than Borisov, perhaps not as far out in the icy reaches of its original star system. Dust analysis has also revealed some surprises. Polarimetric measurements, the way light scatters off tiny particles, indicate that Atlas's dust grains may be coarser than expected, with a size distribution leaning toward larger particles. This affects how the coma and tail appear, and may also say something about the conditions under which the dust was originally trapped in the nucleus. Some models even suggest that the dust has a slightly different reflectivity than that of typical solar system comets, hinting at subtle chemical variations. The chemistry raises an interesting point about diversity. Borisov looked like a comet pushed to extremes, loaded with ices that suggested a very cold nursery. ʻOumuamua seemed to defy classification entirely, with no observable activity. Atlas, by contrast, looks more like a middle case. A comet that's active, rich in CO2 and water, but not dominated by exotic volatiles. That makes it a bridge between the two previous examples, showing that interstellar objects can indeed resemble our local comets, but with their own twists. Spectroscopy continues to refine the picture. Astronomers are hunting for signatures of less abundant molecules like methane, ammonia, and complex organics. Detecting these would be groundbreaking because it would show whether the chemical building blocks of life, carbon and nitrogen-bearing compounds, are common in other star systems. Even the absence of these molecules would be informative, as it would highlight the differences in how comets form across different environments. Every molecule detected in Atlas's coma helps answer the question that began with ʻOumuamua. Are these visitors truly alien, or are they just variations on a familiar theme? The current evidence suggests that while they share a broad family resemblance to our comets, each one carries the unique fingerprint of its birthplace. And with Atlas, that fingerprint is already showing details we've never had the chance to see before. Pinning down the size and mass of a comet is never straightforward, and 3I Atlas is no exception. Unlike a planet or a moon, a cometary nucleus is too small and faint to resolve directly with telescopes. Instead, astronomers infer its size from its brightness and from how much gas and dust it sheds. For Atlas, early estimates suggest a nucleus only a few kilometers across, likely in the 1 to 3 kilometer range. That makes it comparable in size to many of the short-period comets we see in the solar system. Brightness measurements give the first clues. As sunlight reflects off the nucleus and surrounding dust, astronomers calculate an effective size. But this always comes with caveats because the coma can obscure the solid nucleus itself. For Atlas, the variations in brightness as it rotated indicated it wasn't a tiny shard, like ʻOumuamua, which may have been less than 200 meters long, but instead a more substantial body, closer in scale to Borisov. Mass estimates are even trickier. Normally, cometary outgassing causes small but measurable non-gravitational accelerations, tiny deviations from the orbit predicted by gravity alone. For Atlas, however, these accelerations appear to be minimal so far. That suggests its nucleus may be relatively massive compared to its level of activity. If it were very lightweight, like a fluffy snowball, the escaping gases would push it around more noticeably. Instead, the orbit remains remarkably stable. Some researchers have argued this could mean Atlas is unusually dense, or at least more solid than expected. This is especially intriguing in light of ʻOumuamua. One of the central puzzles with that object was its non-gravitational acceleration, despite a lack of visible outgassing. With Atlas, we see the opposite. Clear signs of activity, but little measurable effect on its orbit. That contrast helps sharpen the mystery of ʻOumuamua, while grounding Atlas in more familiar territory. The lack of strong orbital perturbations also helped refine Atlas's trajectory with exceptional accuracy. That makes it easier to calculate where it came from and where it's headed, even if tracing it back to a specific star system remains nearly impossible. From a practical standpoint, a stable orbit also means astronomers can schedule telescope observations with confidence, knowing it won't drift unpredictably. All told, Atlas seems to occupy a sweet spot in size and mass, large enough to sustain visible activity, but compact enough to escape easy detection until surveys became sensitive enough. Its relatively modest size is a reminder of just how many similar objects might be slipping past us every year without notice. With instruments like the Vera Rubin Observatory coming online soon, we may start detecting dozens of these bodies, painting a fuller statistical picture. Atlas may not be a giant, but it's big enough to be scientifically invaluable. By straddling the line between Oumuamua's tiny enigma and Borisov's kilometre-scale comet, it adds a crucial third data point in the growing story of interstellar visitors. Whenever a new interstellar object is discovered, speculation quickly follows. Oumuamua set the tone in 2017, with its odd acceleration and lack of a visible coma, fueling theories that it might be something artificial. By the time 3I Atlas was confirmed in 2025, scientists were ready for similar debates. The first point of interest was its orbital stability. Despite clear signs of outgassing, Atlas showed little in the way of measurable non-gravitational acceleration. For a comet releasing gas and dust, you'd expect its trajectory to shift slightly. That didn't seem to happen here, at least not to a significant degree. This raised questions. Was Atlas unusually massive and dense, so that the outgassing jets barely moved it? Or was there something unusual about how its activity was distributed across the surface? Some researchers, notably Avi Loeb, pointed to this as a curious echo of Oumuamua. In his view, both objects hinted at something odd about interstellar visitors. With Oumuamua, the lack of visible activity, but the presence of acceleration was the puzzle. With Atlas, it was the reverse. Visible activity but little orbital effect. Loeb suggested this could still be consistent with unusual physics, or in the more speculative interpretations, with artificial origins. But the broader scientific community leaned heavily toward natural explanations. Most astronomers pointed out that the level of activity in Atlas was modest compared to comets like Borisov. The amount of material escaping might simply not be large enough to register as a detectable orbital shift, especially given observational uncertainties. Others suggested that the jets might be erupting in directions that cancel out their effects on the orbit, effectively balancing the forces. The artificial hypothesis that Atlas could be engineered or a probe never gained much traction. Unlike Oumuamua, Atlas looks and behaves like a comet in virtually every respect. It has a coma, a tail, and a chemical signature consistent with natural ices. If it were some kind of constructed object, it would be extraordinarily well disguised as a comet, down to the details of its gas emissions. For most scientists, that was enough to dismiss the wilder ideas. What the debates really underscored is how young this field is. With only 3 known interstellar objects, every one of them looks different. Oumuamua broke expectations, Borisov reassured us with something familiar, and Atlas falls somewhere in between. That variety means that any anomaly, whether it's acceleration without outgassing or outgassing without acceleration, feels like a big deal. As the sample size grows, many of these apparent oddities may turn out to be normal variations in a much wider population. Still, the anomalous claims serve a purpose. They push researchers to scrutinize the data more carefully, to rule out biases, and to improve models. In that sense, even the controversial theories keep the science moving forward. With Atlas, the consensus remains that it is a natural comet, but one with properties that make it a valuable counterpoint to both Oumuamua and Borisov. With 3 confirmed interstellar objects now on the books, astronomers finally have the beginnings of a data set. Each one tells a different story, and comparing them side by side highlights just how varied these visitors can be. Oumuamua was the wild card. It looked nothing like a standard comet. No coma, no tail, no visible outgassing. Yet its trajectory showed a small but measurable, non-gravitational acceleration. Its shape, inferred from brightness variations, appeared either elongated like a cigar or flattened like a pancake. And it was tiny, likely no more than a couple of 100 meters long. To this day, Oumuamua remains puzzling because it doesn't neatly fit into any natural category we know. Borisov, discovered just 2 years later, was the polar opposite. From the moment it appeared, it behaved like a textbook comet. It had a bright coma, a long tail, and a composition rich in carbon monoxide, more so than most solar system comets. Borisov was larger, about a kilometre in size, and fragile, breaking apart as it neared the Sun. For many astronomers, Borisov was a relief, proof that interstellar visitors don't all have to be strange. Some can look very familiar, differing mainly in their chemical mix. 3I Atlas sits in between. Like Borisov, it developed a coma and tail, confirming that at least some interstellar objects behave like ordinary comets. But unlike Borisov, Atlas's activity was more modest. It released dust and gases, including carbon dioxide and water, but without the extreme levels of carbon monoxide that made Borisov so unusual. In this sense, Atlas seems chemically closer to solar system comets, yet it also brought its own quirks. Its dust jets included sunward components, and its activity didn't produce much measurable effect on its orbit. Lining them up side by side shows the diversity clearly. Oumuamua, small, inactive, but accelerating mysteriously. Borisov, large, highly active, rich in exotic ices. Atlas, medium-sized, moderately active, chemically normal, but with oddly stable orbital behaviour. This diversity is exactly what astronomers hoped for. With each new discovery, the picture of interstellar objects grows richer. Instead of assuming that all such bodies are clones of one another, we now know they span a spectrum, from bizarre anomalies to seemingly ordinary comets. It also raises the possibility that every planetary system ejects a wide variety of debris into interstellar space. Rocky fragments, icy comets, volatile rich bodies, and everything in between. Another interesting point is detection bias. Oumuamua was small and faint, only spotted because of a lucky survey sweep. Borisov and Atlas were larger and brighter, making them easier to track. That suggests there may be countless Oumuamua-like shards passing by unnoticed, while we're more likely to detect the bigger, more active comets. In other words, our current sample may not be representative of the true population. What ties them together is their importance. Each object provides a unique probe of another star system. Oumuamua hinted at strange physical processes. Borisov pointed to extreme cold formation zones. And Atlas now shows us a comet that feels familiar but still distinct. Together they prove that our solar system is not isolated. Debris from other worlds is constantly passing through, and by catching these messengers, we're getting a direct look at material born under alien suns. Before Oumuamua appeared in 2017, most astronomers assumed interstellar objects would be extremely rare, so rare that we might not see one for decades. The discovery of 3 in less than 10 years completely upended that assumption. If even modest survey telescopes can catch them this often, it means the galaxy is filled with small bodies drifting between stars. Statistical estimates based on Oumuamua and Borisov already suggested staggering numbers. Some studies proposed that at any given time, there may be trillions of interstellar objects within the Milky Way. Each planetary system, during its formation, likely ejects a vast number of comets and asteroids through gravitational interactions with giant planets. Over billions of years, these ejected bodies build up into a galactic background population. The discovery of 3I Atlas strengthens those estimates. It wasn't found because of some extraordinary effort. It was flagged by an automated survey doing routine sky scans. That means similar objects are probably passing through all the time, unnoticed simply because they're too faint or too far from Earth. If anything, the true population is likely much larger than current numbers suggest. The diversity we've seen so far also matters for statistics. If every interstellar visitor had looked like Borisov, we might conclude that most of the galaxy's debris is icy and highly active. But with Oumuamua's inert strangeness on one side and Atlas's moderate, normal activity on the other, we can already see that the population spans a wide range. That variety suggests that no single type dominates. Rocky shards, icy comets, and volatile rich bodies may all contribute significantly. Another angle is detectability bias. Active comets are much easier to spot than inert rocks. Borisov and Atlas stood out because of their comas and tails. ʻOumuamua, small and inactive, was only caught because of a lucky survey sweep and favourable geometry. If most interstellar objects are small and rocky, we're missing the majority of them. Future instruments like the Vera Rubin Observatory, set to begin full operations soon, will be able to detect fainter objects more routinely. Rubin's wide-field deep sky surveys could multiply discoveries many times over. For planetary scientists, the statistical implications are huge. If every star ejects debris as efficiently as we have, then the space between stars is not empty, but teeming with fragments of alien worlds. That means Earth's neighbourhood is constantly crossed by material from far-off systems. The solar system is effectively embedded in a galactic conveyor belt of wandering rocks and comets. In short, Atlas isn't just another data point, it's evidence that interstellar visitors may be common, diverse, and routinely detectable. The challenge now isn't whether they exist, but how many we can find, and how quickly we can mobilise to study them before they vanish into the void. Every interstellar object carries more than just the story of its own journey. It carries clues about how planetary systems form and evolve. 3I Atlas, like ʻOumuamua and Borisov before it, is a piece of material that was once part of another star's planetary system. The fact that we can now study it directly with modern telescopes means we are sampling alien building blocks without leaving the solar system. The leading idea is that objects like Atlas are byproducts of planet formation. When giant planets form, their gravity can destabilize smaller bodies, flinging them out of the system. Our own Jupiter likely ejected trillions of comets and asteroids during the early solar system, sending them into interstellar space. If other planetary systems are similar, then most stars contribute a steady flow of debris to the galaxy. Each interstellar visitor we detect is essentially a messenger from those processes. This ejection mechanism also means interstellar objects preserve a record of where they formed. Borisov's high carbon monoxide content suggested an extremely cold nursery may be far from its star. Atlas, with more normal chemistry, may have formed closer in a region warmer and less volatile rich. By comparing these objects, astronomers can begin to build a catalogue of planetary system diversity, not just through indirect exoplanet observations, but by literally sampling the raw materials. There's also the question of panspermia, the possibility that life's ingredients, or even microbial life itself, could hitchhike between stars on these bodies. While it's a speculative idea, Atlas adds another piece to the puzzle. If interstellar comets are this common, then the galaxy has an efficient transport system for organic molecules. We already know comets in our solar system carry amino acids and other precursors to life. If Atlas or future interstellar visitors show similar chemistry, it strengthens the case that the seeds of life may be widespread and mobile. Another implication is planetary system architecture. To launch an object into interstellar space, you generally need large planets providing strong gravitational kicks. The very existence of a steady stream of visitors implies that giant planets, Jupiter analogues, might be common around other stars. That fits with what exoplanet surveys have shown. Many systems host massive planets, often in different configurations than our own. Each interstellar comet we catch is indirect evidence of those distant giants shaping their systems. Finally, there's the evolutionary angle. The solar system is 4.5 billion years old, and over that time it has likely exchanged material with countless neighbours. Objects like Atlas remind us that no system evolves in complete isolation. Material is constantly being mixed across interstellar space, carrying chemical diversity from one star system to another. In that sense, Atlas is not just a curiosity, it's part of a galactic ecosystem of wandering debris, connecting planetary systems in subtle but profound ways. Even with the wealth of data gathered on 3I Atlas, a number of questions remain unanswered. In fact, some of the uncertainties are the very ones that make this comet so valuable. The first challenge is its origin. Backtracking Atlas's trajectory through space only gives a rough idea of where it came from. Small uncertainties in its velocity translate into vast differences over millions of years of travel. Gravitational nudges from passing stars, giant molecular clouds, and the galaxy's tidal field further scramble its path. Astronomers can say it came from somewhere in the local stellar neighbourhood, but not which star system ejected it. Finding a parent star is close to impossible without a much larger dataset. A second question involves its nuclear structure. We know it's probably 1 to 3 kilometres across, but that estimate doesn't reveal its internal makeup. Is it a fluffy, porous aggregate of ice and dust, like many solar system comets? Or is it denser, with a rocky core beneath its volatile, rich surface? The weak non-gravitational acceleration suggests it may be heavier than expected for its size, but confirming that would require more detailed modelling of its activity. Another puzzle is its activity profile. Atlas shows clear outgassing, but the jets don't seem to alter its orbit much. Why? Are the gas emissions too weak to matter dynamically, or are they balanced in opposite directions? Could there be an insulating crust that only vents gases from localized fractures, limiting the total thrust? These questions highlight how poorly we still understand the physics of cometary outgassing, especially for objects forged under different stellar environments. The chemistry of Atlas also raises questions. The confirmed presence of carbon dioxide and water vapor is expected. But what about other volatiles? Are organics present? Is carbon monoxide abundant at lower levels or truly scarce? Detailed spectroscopy is ongoing, and the answers could reshape theories about where in its home system Atlas formed. If it turns out to be chemically ordinary, that would be just as informative. It would mean many planetary systems produce comets similar to our own. If it's chemically distinct, that widens our understanding of the diversity of planetary nurseries. There's also the broader theoretical issue of population statistics. With 3 interstellar objects detected in less than a decade, how many are really out there? Current models may underestimate their density in the galaxy. If interstellar comets are this common, then either detection efficiency is improving faster than expected, or our galaxy is far more crowded with planetary debris than we thought. That raises further questions about how frequently systems eject material, and what role giant planets play in clearing them out. Finally, there's the biggest open challenge of all: direct exploration. Atlas, like its predecessors, is moving too fast and arrived too unexpectedly for a spacecraft to intercept. The concept of a ready-to-launch interstellar interceptor has been discussed for years, but hasn't yet been realised. Until that changes, we're stuck observing these objects from afar, piecing together their stories indirectly. The theoretical challenge is clear. How do we design missions that can meet these wanderers head-on, in real time, before they slip back into interstellar space? 3i Atlas has already advanced our understanding, but it's also a reminder of how much we don't yet know. Every answer seems to open up 2 new questions. That's why astronomers are watching closely. Not just to learn about this one comet, but to prepare for the many more that are almost certainly coming. Even though 3i Atlas has already provided astronomers with more data than any previous interstellar visitor, its story isn't over. The months around perihelion, when the comet is closest to the Sun, offer the richest opportunities for discovery. As Atlas heats up, new layers of its nucleus are exposed, releasing fresh gases and dust that telescopes can analyse in real time. The James Webb Space Telescope will continue monitoring Atlas in the infrared, where many of the key molecular signatures lie. Webb's instruments are sensitive enough to detect faint emissions of methane, ammonia, and even complex organics. If any of these appear, they could shed light on whether Atlas formed in a region rich in the ingredients for life. Even the absence of certain volatiles will be telling, narrowing down its possible birth environment. The Hubble Space Telescope, though aging, remains valuable for ultraviolet spectroscopy. Ultraviolet light can reveal different aspects of comet chemistry, particularly the behaviour of hydrogen and oxygen. Combined with Webb's data, these observations will provide a fuller picture of Atlas's volatile inventory. On the ground, large optical telescopes in Chile and Hawaii will keep tracking changes in the coma and tail. These observations will show how Atlas's activity evolves as it approaches and then recedes from the Sun. By studying the shape and orientation of the tail, astronomers can model the sizes of dust grains being ejected and even infer the rotation rate of the nucleus. The Atacama Large Millimeter/Submillimeter Array, ALMA, will be key for detecting gases like carbon monoxide and hydrogen cyanide, giving an additional chemical dimension. ESA is also making use of its planetary missions. Mars Express and JUICE have already been redirected to observe Atlas from different vantage points. These spacecraft won't get close enough for high-resolution imaging, but they can provide unique viewing angles and wavelengths that Earth and L2-based telescopes cannot. Together, this creates a multi-platform observing campaign, unlike anything available for ʻOumuamua or Borisov. One of the big hopes is catching outbursts or fragmentation events. Comets often crack or shed pieces as they heat up, and if Atlas does the same, astronomers will have a chance to look at pristine interior material that hasn't been exposed to interstellar radiation for millions of years. Even a modest outburst would be a goldmine of chemical information. Looking further ahead, the Vera Rubin Observatory, expected to start full science operations soon, will change the game. Although it won't be online in time to contribute much to Atlas's study, it will dramatically increase the rate at which interstellar objects are discovered in the coming decade. Atlas may be the last visitor we study with relatively modest statistics. Once Rubin is active, we could go from one discovery every few years to several every year. For now, the goal is to squeeze as much science as possible out of Atlas while it's here. Every observation adds a new layer of detail about its chemistry, its structure, its dust environment, and its behaviour near the Sun. And every new detail brings us closer to understanding how interstellar objects form, evolve, and survive their long journeys through the galaxy. The arrival of 3i Atlas has forced astronomers to step back and reconsider what they thought they knew about interstellar objects. When ʻOumuamua was discovered in 2017, it was so strange that many wondered if it was a one-off oddity, something we might not see again for decades. 2 years later, Borisov showed up and reassured us. At least some interstellar visitors look familiar, behaving like the icy comets we know. But now with Atlas, we finally see a third case, and with it, the beginnings of a pattern. The big paradigm shift is that there is no single template for interstellar objects. Instead, they appear to form a spectrum. On one end is ʻOumuamua, small, inert and mysterious. On the other is Borisov, large, active and chemically extreme. Atlas sits in the middle, modestly sized, moderately active, chemically normal, yet with quirks of its own. The lesson is that the galaxy's debris is as diverse as the planetary systems that produce it. This diversity also reshapes how we think about planetary formation. Before 2017, models of exoplanetary systems were based almost entirely on what we could infer from exoplanet surveys. Now we're sampling the raw leftovers directly, and they don't all look the same. Atlas shows us that at least some other systems produce comets very much like ours, while Borisov suggests that others form comets in extremely cold conditions. Together they imply that there's no universal recipe for building a planetary system. Each star has its own story, written in the comets it throws out. Another shift is in expectation. It's no longer a question of if we'll see another interstellar object, but when. In less than a decade, we've already found 3, despite relying on surveys that weren't optimised for this purpose. With next-generation surveys like the Vera Rubin Observatory coming online, the floodgates are about to open. Atlas may not be the last special case. It may be the first of many interstellar objects studied with modern precision from start to finish. There's also a broader cultural shift. Oumuamua captured the public imagination because of its strangeness, fueling speculation about alien technology. Borisov was a more standard comet and didn't grab headlines in the same way. Atlas, however, strikes a balance. It's not mundane, but it's not inexplicable either. It demonstrates that we can make progress scientifically, fitting these objects into a bigger picture without resorting to sensationalism. The narrative is moving from mystery object to new field of research. Perhaps the most profound change is how we view our place in the galaxy. These aren't just distant signals from exoplanets detected by wobble or dimming. They're physical pieces of alien systems flying through our own neighbourhood, close enough to study with the tools we already have. That changes the relationship between planetary science and astrophysics. It's one thing to infer that other systems exist. It's another to catch their debris in the act of passing by, to measure it, and to compare it directly to the building blocks of our solar system. In short, 3i Atlas doesn't just add another data point, it transforms the conversation. We're no longer in the stage of waiting for the next interstellar object as a rare event. We're entering an era where these objects are becoming a normal part of astronomy, a new class of phenomena to be studied systematically. And that, more than any single measurement, is the real shift Atlas brings. In less than a decade, astronomers have gone from never having seen an interstellar visitor to studying 3 of them in detail. Each one has told a different story. ʻOumuamua, discovered in 2017, baffled scientists with its lack of a coma, its odd acceleration, and its unusual shape. 2 years later, Borisov reassured us that some interstellar objects could look like classic comets, even if its carbon monoxide levels hinted at a very cold origin. And now, 3i Atlas has provided the best opportunity yet. Caught early, observed widely, and studied across the electromagnetic spectrum. Atlas shows that these objects are not just one-offs or curiosities. They are a diverse population. Some will be strange and hard to explain. Others will look familiar, but carry subtle differences that tell us about their star systems of origin. And as we find more of them, we'll start to see patterns emerge. Together they will give us a direct sample of material from across the galaxy, without the need to send spacecraft beyond the solar system. The implications are huge. Interstellar objects reveal how planetary systems form, evolve and interact with their environments. They may carry the raw ingredients of life from star to star, and their very abundance tells us that the galaxy is full of wandering debris, constantly crossing paths with our own system. ʻOumuamua showed us the mystery. Borisov gave us the baseline. Atlas is the bridge between them, proving that interstellar visitors are common and scientifically rich. The next discoveries will only deepen that picture, and with new observatories coming online soon, it's likely we won't have to wait long.